the exponential growth functions. These are going to be functions, of course, like equations. They have exponents in them, and we think about exponents, you know, the base and the power and all that. But with these functions, the base is going to be a number, and the exponent is going to be the variable. So they all look like y equals a times b to the x, where a just cannot equal 0. It could equal 1, it could equal positives or negatives, just not 0. And b, we're going to want to be greater than 1. So if b is a positive number and it's greater than 1, then our functions are going to be growing. Let's take a look at a parent function, y equals 2 to the x. Now we could change the base all we want, but we want to look at the graph and just kind of the characteristics of the exponential growth function. So, how do we graph when we don't know how to graph? Well, we make a table. So, I'm going to pick some x variables, you know, 0, 1, negative 1, maybe 2 and negative 2. So when we plug these in, 2 to the 0 is 1, 2 to the first power is 2, 2 to the second power down here is 4. Remember, with those negative powers, that puts them into the denominator, so 2 to the negative 1 is really a half, and 2 to the negative 2 is 1/4. So with these ordered pairs, let's plot them and see what they look like. Well, 0, 1 is here, and 1, 2 is here. And initially, just after a couple points, we think maybe this thing's going to look like a line, but then we plot some more. Negative 1, a half. 2, 4 is up here. And negative 2, 1/4 is down here. And we see that this thing actually starts to curve. And the exponential growth model actually looks like this. A nice smooth curve that starts very, very small and then gets very, very big quickly. But the y-intercept, it happens at 0, 1. The entire graph stays above the y-axis, but we can use any x values that we want. So, if we think about domain and range, domain is all the x values that we can use, which would be all real numbers. But the range, you notice, are the y values. And the thing about this graph is it stays above the x-axis, so all the y's are going to be greater than 0. Not ever equal to 0, because you can't take 2 to a power and get it to be 0. Now, what happens if we start messing with things like multiplying it by 3? Well, let's take that same table of values that we had, and that was for when y was equal to 2 to the x. Now, for y equals 3 times 2 to the x, we're going to take each of these values and just multiply them by 3. And let's see what happens. Well, 0, 3, 1, 6, negative 1, 3 halves, that's 1 1/2. 4, 12 is very far up here. Oops. Yeah. And then that's 2, 12. And negative 2, 3/4. About right here. And we see what's going to happen is it's going to kind of keep that same shape. It's just that when we multiply it by 3, everything gets 3 times as big, so it just grows quicker. It'll stay smaller for a long time, and then all of a sudden, bam! It's just gonna explode and go get bigger quicker. If it's negative, then what'll happen is that all of those values from the last graph, they're pretty much the same. But now, when we multiply it by negative 3, all of these y coordinates now are going to be negative. I don't need to go through the whole thing, but what will happen is instead of being 0, 3, now it'll be 0, negative 3. Instead of being 1, 6, it'll be 1, negative 6. Instead of being negative 1, 3 halves, it'll be negative 1, negative 3 halves. And what will happen is it'll keep that same idea where it starts small and then all of a sudden, bam, grows really fast. It's just since we have that negative coefficient, it's just going to go below the x-axis. So thinking about domain and range again, once again, the domain is all real numbers, but the range, now instead of being greater than 0, because we have a negative coefficient, all the y values are going to be less than 0. We could also translate, and what I mean by that is if we looked at the parent function that had the y-intercept of 1, 1, 2, 2, 4, and started small and went up like this. When we subtract 1 to the x and we subtract 3 on the outside, we're going to move this thing around just like we always have. So we're going to take all of these points, like this y-intercept that's at 0, 1, and I'm going to move it to the right 1 and down 3. So move it to the right 1 and down 3, and that's where the new point's going to be. And then use that for the next few points. Go to the right 1 and down 3. Go to the right 1 and down 3. And notice we used to have this asymptote right here that was the x-axis. Now it's going to go to the right 1 and down 3. It'll be down here. And so here, let me highlight these points a little bit more. And what's going to happen is all of our points are going to start small again and go up, but we just shifted the graph. Everything went to the right 1 and down 3. The domain is still all real numbers, but the range now, instead of y being just greater than 0, now it's going to be greater than this asymptote that we drew here, 3. Now that was graphing exponential functions. Let's talk more about the actual equations themselves. We have what we call an exponential growth model, and basically what it is that the amount after a certain amount of time is going to be equal to an initial amount times 1 plus the rate to the t power. In class we'll kind of develop this equation a little bit better, but right now I just want to give it to you because so that we can see how to use it. In 1996 there were only 2,000 known computer viruses. During the next 7 years that number increased by 92% each year. Write the exponential growth model for this situation. Well, our amount at any given time, we'll call that V for the number of viruses, is going to be equal to the starting amount. In this case we started with 2,000 viruses. The rate of growth each year was 92%. So we write that as 1 plus 0.92 to the t power. So we can simplify this model into 2,000 times 1.92 to the t. And that'll give us the number of viruses for any year after 1996. So how many viruses were there in 2007? Well, I should really just change this problem, because in the problem it said that this model only works for the next 7 years. So instead of in 2007, let's go with 2003, because that would be 7 years after 1996. So we go ahead and use our model that we just developed right here, and we'll bring it down here. The number of viruses is going to be 2,000 times 1.92, and since 2003 is 7 years after 1996, we're going to go to the 7th power. So we go ahead and just plug that all into our calculator just like it looks, and we'll find out that in 2003 there were 192,370 viruses. Another way that we use exponential growth is when we're talking about money, and the interest model for compound interest is that the amount in an account is going to be equal to the principal times 1 plus the interest rate, except when it's compounded more than once a year, we divide by the n number of times that it's compounded in a year, and instead of raising it to the t, it's n times t. So when we think about our interest being compounded annually, we're going to deposit $4,000 in the account that pays 2.9% annual interest. So the amount in the account is equal to our starting amount, the principal, 1 plus the interest rate, which was 2.9%, and it's compounded annually. How much is the account worth if the interest is compounded annually? Let's say after 2 years. Okay. So then the power that we're going to raise it to is it's compounded once a year for 2 years. So we'll just simplify our expression, 1.029 to the 2nd power. This formula looks a lot like the formula that we just used when we were talking about exponential growth. That's 1 plus r, that was a 1.029 to the t power. That's because it's only getting compounded once a year, right at the end of the year. Anyway, we go ahead and let our calculator calculate this all out, and we find out that the account would be worth $4,235.36. Now, if we compound it quarterly, then we're still going to start with the same $4,000. But now we're going to take that 0.29% or the 2.9% and divide it up to 4 times in a year. That's what quarterly means. Then the power that we take it to isn't just the 2 years, but 4 times 2 years, so 8 times total that it will be compounded over these 2 years. And we let our calculator do all of that work, and we'll see that we get $4,237.97, which is more than if we only compound it once a year, because what we're doing is every time that we compound interest, we're putting interest into the account, and then when we calculate the interest again, we're making interest on the interest that we already put in. Anyway, let's do one more when we talk about the amount in the account if it's compounded monthly. Well, that'd be 4,000 times 1 plus 2.9% divided by monthly would be 12 times a year. The power then that we're going to bring it to is the 2 years times 12 months. Letting the calculator do all the hard work, see that we'll get $4,238.56. So once again, compounding more often gives us more money. And what we need to remember is the compound interest formula.